Hello students, welcome to the class of High Voltage Engineering. So in my previous lectures, we have discussed about the power frequency withstand voltage test and impulse voltage test over the high voltage equipments. Today in this session, I am going to discuss about the partial discharge test on any of the dielectric material. So let us begin. So in earlier, normally the testing of insulators and the other equipment was just based on the insulation resistance measurement, dissipation factor measurement and the dielectric breakdown test measurement. So in previous days, the quality of the insulation will be assessed by either conducting the insulation resistance or by measuring its dissipation factor, or it can be done by measuring only the breakdown voltage capacity. So in case of the dissipation factor, that is broadly known as tan delta value, it has been observed that the tan delta was voltage dependent, so it became a criteria for monitoring the high voltage insulation. So in further investigations, it was found that the weak points in an insulation like the voids, cracks and the other imperfections lead to the internal or intermittent discharges in the insulation, because we know that there always be some kind of the imperfections lies in the dielectric material during its design stages. So these internal imperfections will be the source for the generation of the localized discharge. And the localized discharge, it means that the discharges which are partially occurs. Okay, the discharge which does not bridge the gap between the two electrodes, but it will locally occur. So these imperfections being a small, when not revealed in capacitance measurement, but were revealed as a power loss component in contributing to increase in the dissipation factor. So in modern terminology, these are designated as a partial discharges, which in course of time reduce the dielectric strength or the electrical strength of an insulation, lead to a total or partial failure of the insulation. So if the sites of partial discharges can be located inside the equipment, like in power cable or in a transformer, it will give a valuable information to the insulation engineer about the regions of greater stress and imperfections in the fabrication. So based on this information, the design can be considerably improved, and that is why the partial discharge test plays an important role when one want to understand the design of a given dielectric material, because we know that in high voltage devices the insulation is considered to be the heart of the high voltage equipment. So if any damages occur to these insulations, of course it will reduce the life of the high voltage equipment. So it is indeed requirement for the insulation engineer or the electrical engineer to understand the design perfections of the insulations prior to applying it to the high voltage devices. So this is the some sort of the need of partial discharge test. So let us quickly review two videos to understand about the basics related to the partial failure of the dielectric due to the inclusion of the voids, cracks or any other impurities inside the dielectric material, and successively we will discuss that what exactly the effect that these localized discharge activity will cause and turn the complete failure of the dielectric. So let us start the video.
What is PD? A partial discharge is an electrical discharge or spark that bridges a small portion of the insulation between two conducting electrodes. We call this PD activity. PD activity can occur at any point in the insulation system where the electric field strength exceeds the breakdown strength of that portion of the insulating material. It can occur in voids within solid insulation, across the surface of insulating material, within gas bubbles in liquid insulation, or around an electrode in gas in the form of corona.
So here you have seen the various sites where you have observed the local discharge activities.
Above all, PD activity is the most reliable indicator that assets are deteriorating.
The continuous and high-quality supply of electrical energy is at the heart of our modern economies. Engineers around the world work hard to make this power supply reliable and safe. All major power supply components, such as transformers, cables, generators, and switchgear, need to be kept in perfect operating condition. Their insulation must be able to withstand high voltage stresses. Therefore, it is crucial that its condition can be verified throughout its life cycle. A partial discharge, or PD, is a localized dielectric breakdown of a small portion of the electrical insulation. It can be initiated by voids, cracks, or inclusions within a solid dielectric, at interfaces within solid or liquid dielectrics, in bubbles within liquid dielectrics, or along the boundary between different insulation materials. PD causes the insulation to deteriorate progressively and can lead to electrical breakdown. Insulation breakdown can lead to dangerous situations, severe damage, and ultimately huge economic losses. The affected component needs to be closely analyzed to make sure the PD will not lead to further damage or even complete destruction. Therefore, the integrity of the insulation of high-voltage equipment should be confirmed using PD analysis during its manufacturing, its commissioning, and during its lifetime, so that it stays in good condition and is safe to operate.
So I think you have understand the effect of these localized discharges, and obviously the importance to conduct the partial discharge test to satisfy the design consideration of the given dielectric material prior to its application to the high voltage equipments, then during the installation of the high voltage device, and as well as after some year of its operation as well. So normally when you are performing any kind of the high voltage testings, of course you have to refer the various standards like IEC, then the Indian standards, and so on. So when you are referring to the standards or the standards or the manuals for proceeding the various types of testings, you need to understand some fundamental terms related to those testings. So let us quickly review some important terms related to this partial discharge test. So number one, the partial discharge. So now I can say, of course, it is very much clear to you that what exactly the mean of partial discharge. So electrical discharge, which partially bridge the gap between the two electrodes, is known as a partial discharge. So this partial discharge is likely to be occurred due to the inclusion of the voids or the cracks within the dielectric material. So generally the internal discharges, surface discharges and the corona discharges are normally put up into the category of this partial discharge. Discharge inception voltage, so it represents the lowest voltage at which the discharge of a specified magnitude will occur when increasing AC voltage is being applied. Discharge extinction voltage means the lowest voltage at which the discharges of specified magnitude will appear when applied AC voltage, which is more than the inception voltage, is reduced. Okay, that is known as a discharge extinction voltage. The discharge magnitude, it is the quantity of the charge as measured at the terminals of sample due to the single discharge. The discharge energy, it is the energy which is dissipated by the single discharge. Average current, it is the average value of the current during a cycle due to a single or multiple discharges. The discharge detector, so it is a device used for either detecting or measuring the discharge magnitudes. Okay, so again let us see the video. So the previous terms you always come across with when you are referring the standards to conduct the partial discharge test. So this video will take approximately a 15 to 16 minutes of time, but it gives some kind of in-depth knowledge towards what exactly the partial discharge is. Then we will see how the breakdown will lead to the complete failure by means of these localized discharges.
Okay, so I don't want to go into partial discharge theory too much, and in fact in future sessions I may do some very detailed and dedicated partial discharge theory sessions. However, what I wanted to do is give a brief overview of partial discharge. There is a wealth of knowledge out there, and equally if anyone's got any questions afterwards, feel free to ask. But partial discharge is an electrical discharge that doesn't completely bridge the space between two conducting electrodes. Essentially, you know, if you've got a conductor and you've maybe got another phase, or you've got the earthing point, so two electrodes essentially, a partial discharge is a discharge occurring in between those. So not completely bridging the gap, but occurring at some point in between them. It's a point of electrical stress. It's a point where PD is occurring. I'll go through it in a moment. So PD can occur phase to phase or from phase to earth. So depending on where the defect is, where the problem is in the network, depends on where it occurs, but it can basically occur where you can get a point of electrical stress. So naturally that can be between two phases, heading in different directions if you like, or it can be between phase and earth. It can be in gas-filled voids in solid insulation. It can be in bubbles in liquid insulation, or around electrodes in air, which is known, sometimes can be corona, but can also be surface tracking. So on switchgear, so IPEC tend to focus it on switchgear and cable. Naturally, on switchgear, you tend to get, we classify really as two types. So the first one is surface tracking. So that's when you've got maybe contamination on the outside of an insulator. So you'll get some surface tracking activity, so electrical tracking over a contaminated insulator. The other type is internal discharge. That's where you've got a defect inside a solid insulation. Maybe you've got a crack, maybe you've got a gas-filled void problem from manufacture, or like I said, a crack from damage of insulation, and that's an internal discharge. Now, as you can imagine, with both of those, as you know, with both of those defect types, they can occur across different parts of the network. So they can occur anywhere within a switchgear, if you like, because obviously you've got high voltage running throughout the switchgear, you've got insulation throughout the switchgear, and any component of that insulation could be damaged, which could cause a partial discharge to emerge. Surface tracking is most commonly probably found inside cable terminations, but it can of course occur on bushings and any other sort of where there's a high voltage and then a neighboring open surface. Internal discharge can occur anywhere inside cable terminations, if they're solid terminations, inside the end of cables, inside circuit breakers, inside CTs, VTs, so all different components of the equipment. When it comes to underground cables, the two areas that we see PD activity really, joints and accessories, are by far the most common place to see PD activity. In XLPE systems, so modern cable systems, probably 99, if not 99.5% of PD will be inside the joints. Manufacturing processes now are very accurate, so pure cable PD is very unlikely, and if it occurs, it's probably detected at the time of commissioning or detected at the time of manufacture even. But in the joints and accessories, that's where we're going to find the problems in cable networks. So 99% of PD will be inside joints and accessories. You do get PD in the pure insulation. It can happen. It's much less common with XLPE, like I say, but if you're looking at oil and paper cables, so the older cable types, we still have a lot of that in the United Kingdom, for example, you can find a lot of PD occurring in the oil and paper. However, it's not necessarily always a concern, and I'll come on a little bit about that later. Okay, so the next few slides really go through the mathematical side of PD and why they occur. So I'm not going to go into too much detail, but I will highlight the sort of main impact. So if we take our sort of ideal case, if you like, which is a solid piece of insulation with a perfect defect inside that insulation. Actually, what we're looking at here, why a PD occurs, is not because there is, say, a gas-filled void. It's not because there is gas within the insulation that's causing a lower insulation level. The problem is that the combination of your XLPE or your polymer, your traditional insulation, with a different material, with an air gap, causes an area where you can get an increased point of stress. So the easiest way to explain that is if I look at this slide here. So the breakdown strength of air is 3 kV per millimeter. So over a 20 millimeter air gap, that could withstand a 60 kV insulation. The breakdown strength of this polyurethane, this XLPE essentially, is 10 kV per millimeter, so over a 20 millimeter insulation that could handle 200 kV. However, the problem is that because you've got a combination in our defect here, because you've got some XLPE, then you've got a gas-filled void or an air gap, and then you've got more XLPE. What that means is instead of a uniform dissipation of the energy from the conductor, instead of a uniform dissipation, you get a localized area of capacitance, you get a localized area of stress. So what it means is as the energy in the power cycle increases, the stress very specifically at that defect point increases also. And as that stress increases within normal working voltages, you will get a very small low energy breakdown across that defect. So it must be noted that breakdown is at the defect. It's not across the whole space, if you like. It's just very locally at that defect, and it's a very low energy breakdown. You wouldn't notice it in your electricity network. But what the problem comes from, it acts within working volts. So if we did run through the mathematics, what we would find is that the breakdown strength in this example here is 17.25 kV. So what that means is, whereas, like I said, air would normally withstand 60 kV, the XLP on its own can withstand 200 kV. A combination of the two, this very small air gap, means that at 17.25 kV you get a very small discharge occurring very locally just inside this defect. And so that's what a partial discharge is. It's partially discharging, it's discharging inside that defect. Now the discharges themselves are very low in energy, but it is that repetition in that localized area over time which causes the problems. So as we said, at 17.25 kV is when there's a breakdown, and so this diagram is a little bit complicated, but if you imagine this line here as the line at which the breakdown occurs, so this is our 17.25 kV charge, if you like. What happens is, as the energy in the power cycle is increasing, so if my laser pointer is much easier to demonstrate this. So as the energy in the power cycle is increasing, the stress across that defect is also increasing until eventually it reaches that breakdown point, and then it indeed breaks down. Now the energy in the power cycle is still increasing, and so again we'll get a recharge and a breakdown, recharge and breakdown. So what happens is, on the rising edges of the power cycle, the positive go inside and then the negative go inside, we get an increase in charge, a discharge, increase, discharge, increase, discharge, and then we flip to the negative side, and then we get an increase, discharge, increase, discharge. So what it means is PDs have a very specific pattern in the power cycle. So as the energy in the power cycle increases, discharge will occur both on the positive side and the negative side of the power cycle. So on the right hand side is images that people might be quite familiar with. This is called a PRPD, phase resolved partial discharge, and it's PD patterns in the power cycle essentially. It's one of the tools that is used within a lot of PD equipment, within a lot of instrumentation, to help you decide if the signal you're seeing is from a genuine PD source or from a noise source. It's this distinctive pattern. So here we can see, all we're looking at here is raw data, and each one of these markers is a PD location, but we can very clearly see PD occurring in the power cycle here. So PD, rising edge of the power cycle, falling edge of the power cycle. This one's flipped around the other way, but it's the same thing, rising edge of the power cycle, rising edge of the power cycle. So as the energy is increasing, that's where partial discharge is increasing. Now, of course, this one here on the bottom right hand side is a condensed PRPD, which is quite common as well. It's one power cycle on top of another, so it's quite common of instrumentation to have that functionality. So instead of looking at a single power cycle where there may only be one PD, what you want to do is record data over a period of time, put them all together so that you can see this sort of pattern in the power cycle. Okay. So like I said, every time these small PDs occur, they're very, very low in energy, but they're very localized and they're very repetitive. So the defect point is very small, which means that's why they're very localized, but they're very repetitive over time, occurring multiple times per power cycle. Partial discharge activity doesn't vary between power cycle to power cycle, but it can vary over the day, it can vary over the year. So PD activity shouldn't be viewed as something that only occurs once every 20 power cycles, for example. PD is generally either occurring or not occurring. And generally, if there is a variation with load, that could be a variation throughout the day, or it could be a variation throughout the year. And what you generally find is not so much that PD occurs and doesn't occur. What you'll find is throughout the year or throughout the day, you'll get sort of high PD and low PD. So you'll get a variation of the level of PD, if you like. Regardless, those individual PDs then, they cause a combination of mechanical, thermal and chemical damage, so that over time, basically the defect that was started maybe from an installation problem or a manufacturing problem or some damage on the switchgear, the defect will slowly get worse over time until eventually there will naturally be a catastrophic failure of the equipment. How that damage propagates, or how that damage progresses. If you imagine in solid insulation, it's quite well known, electrical tree will form. So over time, the physical damage to the insulation will form an electrical tree until eventually the electrical tree is so large that the insulation can no longer survive the energy coming from the conductor. Surface tracking, if it's on outside of insulation, you get surface tracking, and generally what you'll see is this sort of carbonization on the outside of your equipment, which is evidence. You also see sort of white pitting as well, so evidence of that sort of surface tracking occurring, of PD occurring on the outer surface of equipment. So consequences of PD, first one is of course cable failure. If you've got a failure inside a underground cable, you'll see a loss of supply, you'll see an unplanned outage, increased CI and CML. CI is a UK measurement, customer interruptions. CML is customer minutes lost. Of course, every country around the world has a similar measurement criteria, basically looking at the impact of the power failure on where the supply is, so whether that's customers or whether that's the industrial side of the business as well. So customer interruptions, customer minutes lost, and of course the failure point must be found. So naturally you need to find where that cable has failed with fault location technology in order to then conduct the repair to bring that system back online. Now with underground cables, that can be very problematic depending on where the cable actually falls. Last minute requirements, in London for example, we can get a 24-hour repair order, emergency repair, quickly shutting down a road, digging the road and repairing the cable. Still very costly, still very inconvenient, if you like, for the wider application. Cables aren't too bad though. Quite a lot of cable networks have redundancy, so a failure of a cable means you can often reconfigure the network. If it's a ring configuration, not a problem. If it's a radial network, that's where the problem comes in, because of course a cable failure is then a loss of supply until that cable is fixed. On the switchgear side of things then, this is quite a dramatic picture. On the wall here, this is actually compound from the cable termination. So this is a compound filled cable termination. This is from London, a picture we took in London. Compound filled cable termination. This is the opposite wall, so it's not carbonization from a large fire or something, even though it looks like that. But it is quite a dramatic picture that I like to use so to emphasize the first point, which is when you have switchgear failure, of course, the first problem is safety implications. So within that substation, you may have other engineers working, and so safety is the #1 problem. When a switchgear fails, it's quite dramatic, and it can be quite damaging to anybody nearby. The other problem is collateral damage. So not only will that main switchgear be damaged, but it could also damage neighboring equipment and neighboring components within your substation. Major disruption, switchgear failures are very costly. They take quite a lot of time to repair, and whilst they are being repaired, of course the reliance or the redundancy is gone. So most substations have 2 sides to the bus bar. If one fails, then one bus bar is shut down while a repair is conducted. It means your redundancy is completely gone, relying on one side of the substation to operate the whole network, and it can be very, very expensive and disruptive. Thank you very much for your time. Hope you learned something, and watch out for new information that we'll be sending through. Thank you.
So I think you have now cleared enough with this internal discharges, what's called as the partial discharge. So let us quickly review that how this discharge will lead to the complete failure of the dielectric materials. So to understand the phenomena of the breakdown because of the involvement of this localized discharge at the cavities or the voids that is being present in the dielectric material, let me first consider a simple geometry where the 2 electrodes are separated by a given dielectric consisting of the internal void as an imperfection. So this red horizontal line normally indicates, let us consider the 2 electrodes which are separated by this green layer of this solid dielectric structure. So here at the 2 sides, likely we are connecting the voltage terminal. So in case of the high voltage engineering, normally to represent or to study the dielectric behavior, obviously we need to ground the opposite terminal, and the one of the electrode is stressed by the high voltage because of the availability of single phase supply. So now let us assume that this solid dielectric is supposed to contain the cavity to its internal structure. Okay, so we cannot say that the insulating materials are always perfectly designed and they are pure and does not cover any kind of the impurity. So ultimately we need to consider them as an impure dielectric material, and impure itself, it indicates some amount of voids or cavity within the medium or at the boundary layers between the dielectrics and the electrodes. So let us assume that this dielectric is consisting of a very narrow crack filled by the air in its design. So these voids are generally filled with this medium of low dielectric strength, and of course the dielectric constant of medium in the void is lower than that of the actual dielectric material. So here I have considered the air as a void. So you know that the air has a dielectric constant of epsilon r is equal to 1, which is lower as compared to the dielectric constant offered by this solid dielectric, which is healthy in portion. Okay, so of course the voltage bearing capacity of this air is very small as compared with the voltage bearing capacity of healthy portion of a dielectric material. Sorry. So the electric field strength in the void is higher than across the dielectric. Under this situation, when we are giving the voltage, the electric field is intensively increased at the void side compared to the field intensity that one can observe in a healthy portion of a dielectric material. So you know that E is equal to V upon D. Okay, now as we are applying a variable voltage, means sinusoidal voltage, where the voltage is being increased from 0 value to its maximum value during the positive cycle as well as during negative half cycle, this electric field intensity is developed across the dielectric material. The value of this electric field intensity, the magnitude of this potential gradient, normally depends upon the thickness of the given dielectric material. So here you can see it's a narrow crack. So we can eventually consider that because of having a lower dielectric strength and lower dielectric constant and the narrow dimensions of this void, the electric field intensity or the potential gradient at this void is very high as compared to the potential gradient or the field intensity which one can observe in this healthy portion. So even under the normal working voltage, the field across the void may exceeds its breakdown voltage value. So as a result it will cause a spark across the void. So it is ultimately known as a breakdown of the void. But yeah, as it is partially occur, as it does not breach the gap between the two electrodes perfectly, it is known as a partial discharge or the discharge which occurs internal to that dielectric material. So it is an internal discharge. So life of the insulation with this internal discharge depends upon the magnitude of applied voltage and the number of discharges that is being observed. Okay, obviously it depends upon the type of the applied voltage. So generally if we are considering our electrical system network where we are using alternating cycle source, okay, AC voltage, so it means that it will be very easy enough for the testing engineer to calculate the number of discharges, and this number of discharges always occurring during the positive half as well as during the negative half, which you have seen in this video as well. So life of that insulation with this internal discharges or with these partial discharges or localized discharges depends upon the applied voltage and the number of discharges. So breakdown by this process may take place in few days or it may take few years as well. So this circuit is actually representing the equivalent circuit diagram for the insulation with internal discharges. So electrical insulations with imperfections or voids leading to the partial discharges can be represented by this circuitry. Okay, so let us consider that the capacitor with a void inside the insulation is represented as C1. The capacitance of the void is represented by a capacitor in series with the rest of the insulation's capacitance. So here C1 that is being shown actually in series with the capacitance which is offered by the healthy portion of capacitor C2. So C2 is nothing but it is the equivalent capacitance of the capacitor that you are being observed in series with this C1. Okay, so C2 is the series combination of capacitance at this part and capacitance at this part. C3 is the capacitance of healthy capacitor which is in parallel with the capacitance of C1 of the void. So C3 is nothing but it is the equivalent capacitance of capacitor that you can observe at the capacitance at this side and capacitance at this side. So if I am drawing a real picture for this, then it can be represented like this. So this is suppose C31 and this side is C32. So this parallel combination of C31 and C32 will give this C3. Now the void capacitor I need to show it. So prior to that I have to also show the series capacitances. So suppose this is C21 and in between C21 and C22 that is the capacitance of void. So this is your C1 and this now comes C22. So series combination of C21 and C22 will give C2 and of course this is C1. So this circuit can be reduced to this form. So one can also simulate this partial discharge circuitry in the MATLAB as well to observe the discharges across the dielectric material when it is subjected to heavy stresses. So generally we can write the relationship between all these capacitances as C1, of course it is obviously very much less as compared to the capacitance which you can see in series with it, and that series capacitance is also very much less as compared to the healthy portion which is in parallel to the series combination of healthy capacitance and the void capacitance. So if you are considering the relationship between C1 and C3, then C1 is negligibly small as compared to the capacitance that is being offered by this C3. Okay, so normally when we are giving the voltage over the screen of the CRO, one can observe this kind of the wave shape. Okay, so here V, that will represents the alternating voltage. So as you can see that as the voltage is being increased to a peak maximum, to a maximum value, the voltage across this capacitor C1, the voltage across this capacitor C1 is also increasing. It means that now the capacitor is charging when the voltage is being applied. So as the input voltage is increasing, the potential across the capacitor also increases up to its discharge inception voltage magnitude. Okay, so when the voltage across this capacitor becomes equal to its breakdown capacity, the breakdown of C1 takes place, the breakdown of the void takes place. As a result, the voltage across it will reduce, because as the discharge takes place, it will release the energy which it has stored during the increment of the supply voltage. So because of the discharge of that capacitor C1, you can observe there is a peak in the current value. Okay, ultimately as you can see that the sparking between the two sides of the void is shorted. So as a result, the current is increasing, okay, and the voltage is reduced. At the same time, as the voltage is still increasing, the potential across the cavity increases, and again the discharge will take place when the voltage across it becomes equal to its breakdown value. So again one is observing the current peak as well. Okay, so when the supply voltage becomes lower than the voltage across the capacitor, no discharge is being observed, because as you can see that from peak magnitude during the positive half cycle, from peak magnitude the wave shape is now wave is trying to move towards the negative side. So after some period of time, the supply voltage magnitude becomes lower than the voltage across the capacitor. So in that cases, the voltage in this stage the capacitor will not fully charge. As a result, no discharge has been observed. As there is no discharge, the current is zero until the next discharge. Okay, so again the process will repeated in the negative half cycle as well. So capacitor will charge and then discharge, charge and discharge, charge and discharge. So as a result, the current is also can be observed, but towards the negative polarity. Okay, and the process is repeated. So here you can see that the discharge activity is repetitively observed when it is subjected to the alternating cycle. Okay, so the number of discharges that one is observing during the positive half cycle is also equals to the negative half cycle as well, but only in one condition: if the applied wave shape is pure. If suppose it is impure, then the number of discharges in positive half cycle and negative half cycle may get differ. So internal discharges have the same effect as one can see in the traying phenomena, the breakdown due to traying in insulation. So when the breakdown takes place in the void, the electrons and positive ions are generally formed. Let me zoom that figure, okay, to understand the concept of this traying phenomena. Let us assume that this is the void, and suppose this is the complete solid dielectric, and internal to it, suppose there is an air gap. So when the breakdown occurs in the void, the electrons and positive ions are formed. So let us assume that the electrons and the positive charges are getting produced due to this discharge. So now these electrons and the positive ions have sufficient energy, and when they reach to the surface of the void, they may break the chemical bonds. Okay, so suppose now these electrons and these positive charges are colliding with the inner surface, with the inner surface of the void. Okay, so they are continuously targeting or colliding with the inner surface, where you can observe the mechanical kind of the damages due to this ionic bombardment phenomena. So this space charges will now colliding continuously to this inner wall of the void, and as an effect it will break its chemical bond. So let me first wipe out this. Okay, now let me draw the narrow kind of figure. Okay, so suppose here the sparking is occurring. As a result, the ions are produced, and these ions will cause a mechanical kind of damaging effect to the inner wall of this void. Okay, so because of this because of this the chemical bond of this void is getting eliminated. So in each discharge, again there will be some heat is dissipated in the cavity, and this will carbonize the surface of void and will cause the erosion of material. So eventually again there is an erosion. Okay, so erosion will take place. So ultimately it will try to extend the dimensions of the air gap. The another mechanism that one can observe is channels and pits formed on the cavity surface, which increase the conduction as well. So channels is nothing but the tracking, which you have probably seen in the video, that how the electrons are trying to bridge the gap. Okay, so ultimately once the tracking has been established, one can observe the tracking as well, the channels. And because of this the conductivity electrical conduction is also increasing. Okay, so one is that when the partial discharge takes place, the electrons and positive ions are formed, and these electrons and positive ion makes the ionic bombardment, the mechanical deformation to the inner wall, which breaks the chemical bond. So the another point is during each of the discharge, there always be some amount of heat is being dissipated in the cavities, which will carbonize the surface of the void and cause the erosion of material, which eventually increases the dimension of the crack as well. Because of this training phenomena, because of the distribution of these electrons, the channels are produced and pits are produced over the cavity surface, which increase the electrical conduction as well. The chemical degradation may also occur as a result of these active discharge products produced during the breakdown of this crack as well. So all these effects will result in gradual erosion of material and consequent reduction in thickness of the insulation, which leads to the complete failure. So initially this will be the dimension of the crack. Because of this partial discharge activities, because of the localized discharge which is acting continuously, it will erode the material and gradually reduces the thickness of a solid dielectric material, and at the end it will bridge the gap between the two electrodes and causes the permanent failure of an insulation. So this is the a process that how this internal discharge will lead to the complete failure of the insulation. So in next lecture we will see the other parts of this partial discharge. So here in this lecture I have discussed about the some basic things related to the partial discharges and how it will lead to the failure. In this video I have also represented the some experts video informations related to this partial discharges. I will share the links for those videos in the description of this session to impart in depth of concept. So in next part we will see the partial discharge test circuits. Okay, partial discharge test circuits, then the discharge detectors, and also I am going to touch upon the how the partial discharge test on the cable is being conducted. Thank you.